We know around any nucleus of charge Ze, an electron revolves in a stationary orbit. When an electron is revolving in a stationary orbit, it does not lose the energy. Now, if an electron jumps from any of the higher energy stationary orbit, any of the higher energy orbit to a lower energy orbit, this electron liberates the energy, loses the energy. How much of energy will be lost in the form of electromagnetic wave? The energy lost is the energy difference between the orbits. That is, if the electron in the higher energy orbit has a En2 energy and in the lower orbit En1 amount of energy, the energy difference is liberated. That is, En2 minus En1, energy of the higher orbit minus energy of the lower orbit, is liberated as a photon, as an electromagnetic wave. The energy of the photon is h nu. Or otherwise, we can say it is hc by lambda. So we needed an expression for wavelength. So hence let us consider this part of the expression and finally derive for lambda. So hence therefore hc by lambda is equals to En2, where N2 is the quantum number of the higher energy orbit, N1 is the quantum number of the lower energy orbit, En2 minus En1. We know the expression for the energy, total energy, we just got it. So therefore, hc by lambda is equals to, what is the En2? Minus m z square e power 4 divided by 8 epsilon naught square N2 square h square is energy of the En2, the higher energy orbit, minus m z square e power 4 divided by 8 epsilon naught square N1 square h square is the energy of the lower energy orbit. Now rearranging the terms here, hc by lambda is equals to, let us take the common here. What is not common between these two terms is N2 and N1. Retaining those terms, rest of that common can be taken out. Hence, m e power 4 into z square divided by 8 epsilon naught square h square into 1 by N1 square, minus into minus, the second term becomes positive. Therefore, the positive term is written first, 1 by N1 square. The first term has a negative sign, written as the second term, minus 1 by N2 square. Further, again if you observe this bracket, this all got constants. Let us bring the other constant to the left hand side, that is hc, which is also a constant, move to the right hand side. Then you get 1 by lambda is equals to 1 by lambda, that is reciprocal of wavelength, is also called wave number nu bar. Reciprocal of wavelength is a wave number nu bar, that is equals to me power 4 divided by 8 epsilon naught square. I have brought the c down here to the second side and the h also down, cross multiplied here to the h square, and therefore becomes h cube, me power 4 divided by 8 epsilon naught square ch cube into a z square into 1 by n1 square minus 1 by n2 square. Observe now, this whole of this bracket has got only constants. All these constants together will be called something called Rydberg constant. Therefore, we can say where me power 4 8 epsilon naught square ch cube is called Rydberg constant, whose value therefore, after substituting all these values and simplifying, will become 1.097 into 10 to the power of 7 per meter. 1.097 10 to the power of 7 per meter. Anyway, getting back to this expression, the wave number nu bar, or otherwise reciprocal of wavelength lambda, therefore can be written as r z square. Rz square into 1 by n1 square minus 1 by n2 square. So this entire bracket has become the Rydberg constant R, and Z is retained there. So this is the expression for wave number of any spectral line emitted by an electron transition in a given atom. But since the theory proposed by Bohr is applicable only to hydrogen atom or hydrogen-like atoms, for hydrogen the Z value becomes 1. Hence the wavelength at the new bar is equals to R into 1 by n1 square minus 1 by n2 square. So this is the final expression for the wave number R reciprocal of the wavelength, or otherwise called wave number of a spectral line or wavelength of a spectral line. Now by knowing from which orbit to which orbit the electron is undergoing transition, is it from second orbit to first orbit, or fourth orbit to second orbit, or any nth orbit to a given orbit, when we know the n1 and n2 values, that is the quantum numbers when we know the principal quantum numbers, we will be able to calculate the wavelength emitted during that particular transition. Our wave number can be calculated by knowing the orbits between which the transition is taking place. So with this, all the required derivations of this chapter comes to an end. We still have the energy level diagram, the hydrogen spectrum, and the merits and demerits of the Bohr's atom model. Students, let us continue. We have derived expression for radius of a stationary orbit, velocity of an electron in a stationary orbit, even the total energy. Finally, we even got the expression for wave number or wavelength of a photon emitted whenever there is a quantum transition of an electron from the higher energy orbit to the lower energy orbit. Now, let us discuss the energy level diagram and the hydrogen spectrum, or the spectral series of the hydrogen atom. Energy level diagram. Energy level diagram. We know the energy of an electron in any orbit is minus 13.6 electron volt Z square divided by n square, and for hydrogen atom we know it that En is equals to minus 13.6 electron volt divided by n square. Now you observe, as the principal quantum number, that is the orbit number, as this increases, the energy of the electron decreases or increases. You can observe the negative sign here. If there was no negative sign with the orbit number, energy would decrease. Whereas now, since there is a negative sign, the negative energy decreases, which implies that the positive energy increases. Therefore, as the orbit number increases, the energy of the electron also increases. Or otherwise we can say the negative energy decrease. As the negative energy decrease, we can say from the negative energy, the energy of the electron is approaching zero. This variation we can understand from the energy level diagram. We will say right now, if n is equals to 1, for n is equals to 1, we know the energy of the electron, that is in the very first orbit, it is minus 13.6 electron volt. Say we will take one more orbit here, n is equals to 2. For the second orbit, say E2 is equals to minus 3.4 electron volt. That is, this divided by 2 square will give you minus 3.4 electron volt. Go to the third orbit now, that is energy in the third orbit, E3 is equals to minus 1.51 electron volt. What are we doing? We are dividing this by 3 square, minus 1.51. Observe now, as the orbit number is increasing, the negative energy value is decreasing, or otherwise the electron is gaining more and more amount of energy. Also, we should notice one more change between the energies of the first orbit and second orbit. The difference is around 10 electron volt, say 10.2 electron volt. And observe here, this energy difference is less than a 2 electron volt. Again observe here, this energy difference is around 0.75 electron volt. So the energy difference between the adjacent energy levels is decreasing as the orbit number increasing. So based on this, now we can roughly draw an energy level diagram. Minus 0.54 electron volt and so on, this goes. So roughly you can take this value. Of course you can, since we have the expression, you can calculate energy to the following energy levels. So similarly, if you go on increasing the orbit number like this, let's go to n is equals to infinity. L is equals to infinity. That is, when the principal quantum number, the orbit number becomes infinity, minus 13.6 electron volt divided by infinity, any number divided by infinity becomes a 0, which means an infinite orbit should have a 0 energy. Where will this infinity be? Anything, say you take minus 13.6 electron volt divided by 25 square or 625, or maybe say 100 square. So if you take such a orbit with large quantum number there, the energy is almost 0, nearly 0. So where will that orbit be now? This idea we can actually get from the energy level diagram. Let us now draw the energy level diagram. Let's say the very first orbit, we call it as a ground state. Say n is equals to 1 with an energy of E1 is equals to minus 13.6 electron volt. Now go for an n is equals to 2 with how much lesser amount of energy? We have already seen that by how much more amount of energy, in fact, that is 13.6, 3.4. The energy difference is around 10.2 electron volt. So by 10.2 electron volt energy rises. So n is equals to 2. The energy E2 is minus 3.4 electron volt. If you go to n is equals to 3, once again you observe the energy difference slightly less than a 2 electron volt here, which means if this is a 10 units of space, 10 electron volt difference, and we should have just a 2 electron volt space. Let's just draw it roughly. Let's not go for the measurements here anyway between the two energy levels here. Let's say this is n is equals to 3. So n is equals to 4 should be much even closer. N is equals to 5 should be even closer. So the orbits are getting closer and closer and closer. 6 should be even closer. 7 should be even closer. And so on. If you go to the higher levels right now, they appear almost like a continuum. Say somewhere here we get the infinity. Infinity is not too far away in terms of energy right now. The reason you see the energy difference between n is equals to 1 and n is equals to infinity is just 13.6 electron volt. It can't be too far away from the nucleus. The infinite orbit can't be too far away from the nucleus, and within which we have infinite energy levels. Therefore, between n is equals to infinity and those lower energy levels, the remaining energy levels appear almost like a continuum. So this is called the energy level diagram. From the energy level diagram, we in fact can study the line spectrum of the hydrogen. So from here itself, let us also discuss about hydrogen spectrum or hydrogen spectra, the plural of spectrum. Okay. Here we need to understand the word spectrum. What do you mean by spectrum? The orderly arrangement of the wavelengths or otherwise the energies or momenta is called the spectrum. What do you mean by the orderly arrangement of wavelengths here? We all know whenever any electron jumps from a higher energy orbit to a lower energy orbit, the electron liberates the energy difference between those two levels as a photon, as an electromagnetic wave. Now when we observe this photons emitted, this light emitted through a spectrometer, we will be seeing a spectrum. What is a spectrum therefore? What kind of spectrum do we observe? We will be observing a line spectrum. Line spectrum will have a dark background over which we will have few bright lines. Each line there corresponds to one photon emitted, which is nothing but one transition of the electron. Every transition of the electron will be emitting a particular photon. That photon will be appearing like a bright line on a dark background. We call this as a line spectrum. That's why the hydrogen spectrum as an atomic spectrum is a line spectra of hydrogen. Therefore we can say line emission spectrum Alternately, we can call it as a line emission spectrum. So we will take singular for some time in our discussion. So line emission spectrum. Now here in this line emission spectrum you will have few different radiations are present. So you can have visible light present in the spectrum, you can have ultraviolet light present in the spectrum, you can also have infrared radiations present in the spectrum, based on from where to where the transitions are taking place. Now carefully listen here. When we consider the hydrogen gas and excite the hydrogen gas, different hydrogen atoms will be excited to different higher energy levels. Some hydrogen atoms will go to the second state, some hydrogen atoms will go to the third state, and some to the fourth state, some to the fifth state. So different atoms, different number of atoms are there in the different energy levels. Now these atoms which are excited cannot stay in the excited state for a long amount of time. In about 10 to the power of -8 to -7 seconds or -6 seconds, they have to de-excite and come down to the ground state. The natural tendency of all the systems to be in the ground state itself. Therefore, even though you excite it by heating it or by supplying some energy, even though you excite the gas, the atoms go to the excited states and spontaneously they come down to the ground state. While coming down, some of the atoms which were excited to different states may directly come down to the ground state. Without passing through any intermediate states, they can directly come down to the ground state. Therefore, they all emit one particular kind of the electromagnetic waves. If they come down directly to the ground state, just like this, say if they come down directly to the ground state, from second orbit to the third orbit, a few atoms are coming like this from 2 to 1, you say. Few more atoms are coming down from 3 to 1. Some more atoms are coming down from 4 to 1. They may come from anywhere but to the n is equals to 1 state. They all can emit one particular kind of the radiation. The kind of the radiation they emit is the ultraviolet radiations. And each of this emission will be appearing like a bright line in the line emission spectrum. The spectrum therefore that you get was discovered by a scientist by name Lyman. Hence, this spectrum is named after this man, and the spectrum is called Lyman series of spectral lines. Now, the very first transition you observe in the spectrum, that is n is equals to 2 to 1, has the smallest energy difference between 2 to 1. You know what is energy difference? The energy difference is around 10.2 electron volt. And the biggest transition in the spectrum is from n is equals to infinity to 1. The biggest transition, that is the biggest energy difference. So the smallest transition will give you least amount of energy, whereas the biggest transition will give you highest amount of energy. The least energy, if energy is minimum, you know that E is equals to hc by lambda is the energy of a photon. If the energy is minimum, the wavelength emitted is maximum. Therefore, here it will be emitting a maximum wavelength. This is lambda maximum. Whereas the biggest transition here is between infinity to 1. So if the biggest energy difference is 13.6 electron volt, you can observe between E1 and E infinity the energy difference is 13.6 electron volt. If the energy difference is highest, the wavelength emitted will be least. Therefore, the last transition of the series will be emitting the least wavelength. Smallest wavelength it will be emitting. We call this as lambda minimum. This lambda minimum of that series is called also series limit. That is a transition from infinity to 1 is called the series limit of the Lyman series. So now all that we have discussed in this spectral series is the transitions from anywhere to n is equals to 1. We call this Lyman series. Supposing if the transitions happen, if the de-excitations complete on n is equals to 2, that is, there are a lot of atoms which are in different states. All those atoms, if they end their transitions and n is equals to 2, if the transition completes and n is equals to 2, you will be getting a different kind of electromagnetic radiation which is in visible range. So visible light will be emitted if the transitions complete and n is equals to 2. Say for example, from 3 to 2, 4 to 2, you can have a 4 to 2, you say, 5 to 2, 6 to 2, or even 7 to 2. All these transitions will give you one particular kind of radiation, that is visible light they will give you. visible light. And this was discovered by a scientist by name Balmer, a Swiss school teacher. Even before the electron was discovered, the spectrum was observed by this great man, Balmer. And this is named after by the same scientist, hence we call this as Balmer series of spectral lines. Therefore, for the series to be called Balmer series, the transition should be completed where? The transition should be completed on n is equals to 2. From where? From 3, from 4, from 5, from 6, from anywhere. Once again, even in this series, you observe there is a smallest transition. The smallest transition is therefore between 3 to 2. Between 3 to 2, you can observe there is slightly a less than 2 electron volt energy. An energy difference is 2 electron volt. If the energy is minimum, the wavelength will be maximum. Once again, therefore, this photon will have a maximum wavelength. You say lambda maximum. And similarly, if the transition happens from n is equals to infinity to n is equals to 2, this transition is the biggest transition of that series. The biggest transition of that series is therefore between 2 and infinity. You observe the energy difference between 2 and infinity. Between 2 and infinity, the energy difference is about 3.4 electron volt. So this will give you a 3.4 electron volt, whereas this one will give you slightly under 2 electron volt. So this is 2 electron volt is smaller, 3 electron volt is larger. So the larger energy means a smaller wavelength. Therefore you get a smaller wavelength here. We call this as lambda minimum. Any lambda minimum of a series is called again series limit. So you have a maximum wavelength and the minimum wavelength of Balmer series. So Balmer series is in visible light. Lyman series is in ultraviolet radiations. Say ultraviolet radiations. Similarly, if the transitions terminate at n is equals to 3, we have a different series. We call it as Paschen series. Say the transitions complete on n is equals to 3. 4 to 3, 5 to 3, 6 to 3, 7 to 3 and so on, even from we can say infinity to 3. So this series of spectral lines is called Paschen series of spectral lines. Paschen series. The radiation emitted is in near infrared radiation. Near infrared radiation. Okay, once again the smallest transition will give you minimum wavelength. So we can say this is lambda minimum, whereas this one is called, this is called lambda maximum, this is called lambda minimum. So smallest transition is the smallest energy difference, will be emitting you maximum wavelength, whereas the biggest transition means biggest energy difference, which will give you minimum wavelength. In a similar way, we can also have two more spectral series of hydrogen atom. The next spectral series will be produced if the transitions terminate on n is equals to 4 and n is equals to 5. So if transitions terminate on n is equals to 4, 5 to 4, 6 to 4, 7 to 4, 8 to 4, even from infinity to 4, from any orbit to the fourth orbit if the transition completes, then we get a different spectral series. This spectral series we will call Brackett series. Brackett series. Brackett series will be emitting infrared radiations. The light in the Brackett series is the infrared radiations. Similarly, the last spectral series is called the Pfund series, or otherwise Pfund series, where we can say P can be kept silent in our pronunciation. Therefore, this last series can be obtained by all the transitions that terminate on n is equals to 5. If the transitions terminate on n is equals to 5, then the series is called Pfund series. Even there we can have the smallest transition and biggest transition. Always the smallest transition will have least energy. Least energy means the maximum wavelength. Biggest transition means highest energy. Highest energy meaning the smallest wavelength. Similarly, even here the smallest transition will give you maximum wavelength. Biggest transition will give you minimum wavelength. And the spectral series, as I said, it is a Pfund series or Pfund series, named after by the scientist who discovered it. This will be in far infrared radiation range. far infrared radiations. In every series, the biggest transition, as I told you, is called the series limit. That is, a minimum wavelength is called the series limit of that particular transition. Now, applying the wavelength expression that we have already derived, the wavelength reciprocal of wavelength 1 by lambda is r into 1 by n1 square minus 1 by n2 square. If we apply this relation to all the spectral series, now you observe the n1 and n2 values, if you apply to this particular series, n1 will always remain 1, whereas n2 will take 2, 3, 4 up to infinity. Now it's quite easy for anyone to guess what should be n1 value for the Balmer series and remaining n2 values. Similarly for Paschen, Brackett and Pfund series. So what should be n1 value for Balmer series then? Since the transitions are terminating on n is equals to 2, n1 should be 2. Of our expression n1 should be 2, whereas n2s should be 3, 4, 5 and so on. They should go up to infinity. So this is for Balmer series. Similarly for Paschen series, if you apply, n1 should be 3, n2 should therefore be 4, 5, 6 and up to infinity. Whereas for Brackett series, n1 is 4. So for Brackett series, the n1 value is 4, n2 value is 5, 6, 7, goes up to infinity. Whereas for the last series, that is Pfund series, which always completes, the series completes on the orbit number 5, the n1 value should therefore remain 5 and the n2 values should be 6, 7, 8 and goes up to infinity. So hope we have understood, we have followed which series is from where to where and what are the n1 values, n2 values and which range of the electromagnetic waves are emitted. With this we have understood the hydrogen spectrum or the line emission spectrum of the hydrogen atom. So with this, almost the entire theory part of the hydrogen atom is coming to an end. Now we will see the merits and demerits of the Bohr's atom model, otherwise Bohr's theory of hydrogen atom. What are the merits of the Bohr's theory of hydrogen atom? Merits of the Bohr's theory of hydrogen atom. Of course, Bohr's theory of hydrogen atom is a very first successful atom model. Based on Bohr's theory, we could explain the stability of the atom. That was a biggest problem in case of the Rutherford's atom model. Bohr's theory gave the stability to the atom. Point number 2, it explained the charge neutrality. Charge neutrality. That is, the amount of positive charge is always equal to amount of negative charge in a stable atom. Bohr's theory explains that. Merit number 3, we could derive expression for radius of the orbit. We could even get the velocity of an electron, kinetic energy, potential energy, total energy, and even the wave number or otherwise wavelength. These expressions we could derive based on Bohr's postulates very precisely. So it is another great success that we could even calculate radius, velocity, kinetic energy, potential energy, total energy, even wave number. All these can be calculated based on Bohr's postulates. Merit number 4. Now Bohr's atom model is able to explain the hydrogen spectrum, which is another great success. After stability of the atom, hydrogen's theory, the Bohr's theory, is able to explain even the hydrogen spectrum. Another great success because in the earlier atom models like Thomson's atom model, even the Rutherford's atom model couldn't even explain a small part of the spectrum, the hydrogen spectrum or the spectrum of any atoms. These are some of the very important merits of the Bohr's theory of hydrogen atom. In spite of these merits, the Bohr's theory sought some of the failures, or otherwise you can say limitations or demerits. What are the demerits? Demerits, or we can say limitations. What are the limitations of the Bohr's atom model? Bohr's theory of hydrogen atom is applicable only to hydrogen atom or only hydrogen-like atoms. We cannot apply the Bohr's theory of hydrogen atom to many electron systems. If you have a single electron system, an atom with only single electron, then the Bohr's theory is successful. For many electron systems, it is not applicable. Therefore, demerit number 1, this theory cannot be applicable to many electron systems. That is, Bohr's theory is applicable only to hydrogen and hydrogen-like atoms. It can be presented, this point can be presented even like that. Failure number 2, or limitation number 2. Even though Bohr's theory explains the hydrogen spectrum, the spectral lines were explained, the fine structure of the spectral lines were not explained. Fine structure is not explained. Fine structure is not explained. What is a fine structure then? If you observe any one spectral line with an ordinary spectrometer, it will appear just like one bright line against a dark background. If you take a very powerful spectrometer, if you observe that spectral line there, it appears like a pack of very fine lines, a few fine lines. Why? It's like one spectral line is a pack of fine thin spectral lines is not explained by the hydrogen's theory, the Bohr's theory of hydrogen atom. Failure number 3, the relative intensities and positions were not explained. Relative positions and intensities. Relative positions and intensities of spectral lines were not explained. In the sense, Bohr's theory couldn't explain why there is an intensity variation in the spectral lines, that was not explained, and why exactly these spectral lines were positioned in those positions also was not explained. So these are some of the important failures. The biggest failure is that it was not applicable to many electron systems, it was applicable only to a single electron system. Last point to conclude the chapter. In Bohr's postulates, we have seen the angular momentum quantization condition. That's the second postulate of Bohr. What was the second postulate of Bohr? Bohr proposed that the angular momentum is integral multiples of h by 2 pi for an electron in any stationary orbit. That is, the angular momentum of an electron in any nth stationary orbit is equals to integral multiples of h by 2 pi. We often call this as the puzzling postulate of Bohr. What is the reason for it? Bohr even did not explain why it should be like this. Why should the angular momentum be integral multiples of the h by 2 pi was not explained Bohr himself. But only if the angular momentum is like this, the atom becomes a stable atom, the atom becomes the right kind of the atom, and the whole of that we have discussed can be done only if the angular momentum is like this. Why? It was not explained by the Bohr. But who explained this? Later on, Louis de Broglie, should be pronounced as de Broglie. This man in the year 1924 explains the significance of the second postulate of the Bohr. So how does he explain this? Now we know the angular momentum L is mvr is equals to nh by 2 pi. Why should it be like this? Now Louis de Broglie in fact was a successful man in proposing the dual nature of material particles. According to him, every material particle possesses dual nature, that is both particle nature as well as wave nature. Now applying this theory to the hydrogen atom here, suppose if you have the nucleus and say the electron is revolving around the nucleus, this electron which is in motion, according to de Broglie's theory of dual nature, this electron as it is moving should move like a wave. Otherwise there must be a wave associated with this moving electron. If there has to be a wave there, how can the postulates proposed by Bohr be compatible with what Louis de Broglie said? How can they co-agree with each other? If they have to co-agree with each other, then L should only be L is equals to nh by 2 pi. If it was something else, if it is not nh by 2 pi and if it is something else, then both the theories cannot co-agree with each other. and de Broglie says that they are co-agreeing with each other just because L is equal to h by 2 pi. The explanation goes like this. We know that the wavelength of matter waves, wavelength of the waves associated with moving particles is lambda is equal to h by p as proposed by de Broglie, which we have seen in the previous chapter. It is h by mv. If this has to go right, say for example, if n is equal to 1 orbit, in the very first orbit, then how should the electron look like? What kind of wave is present there? Just to check that back, get back to this expression here. In this expression we have mvr is equal to h by 2 pi. We will move this 2 pi to the numerator of the first side of the equation and mv move down to the other side. Then it becomes say 2 pi r. From this equation 1 we are just doing this. Equation 1 is giving us this, that 2 pi r is equal to nh divided by 2 nh divided by mv. 2 pi is shifted to the numerator, mv is shifted to the denominator, the other side. Now you see, mv is nothing but p again. It becomes h by p, n times h by p, where h by p is the wavelength. Therefore, the 2 pi r is equal to n times the wavelength from the de Broglie's theory. 2 pi r is the circumference of the orbit. Therefore, every orbit, the circumference of each orbit is equal to n number of wavelengths. We already know what is n there, which is a principal quantum number. If you take n to be the first orbit, in the very first orbit, therefore, the entire circumference should be arranged like one full wave, one full wavelength of the matter waves. Suppose if it is a second orbit, then the circumference of the second orbit, say this is the nth radius. For a second orbit, therefore, circumference of second orbit is divided as 2 wavelengths. In a similar way, third orbit should be 3 waves and fourth orbit should be 4 waves. In a much similar way, when the electron goes around the nucleus in an orbit, it should appear like a stationary wave. The electron should be going like this, should be going like this. Therefore, if this continues, if the electron continues, the electron should move in a path like this, that is in a circular path like this. The circular path is divided now into n number of waves, that is matter waves. With this, de Broglie explained the significance of the angular momentum quantization condition as proposed by Niels Bohr. Students, let us now do a few important numericals from the atoms chapter. One of the very important numerical is to calculate minimum and maximum wavelengths of given spectral series. Calculate minimum and maximum wavelengths of Lyman series, similarly Balmer, Paschen, Brackett and Pfund series. One series, let me solve here. Similarly, based on the same, you can solve for the remaining series. Say for Lyman series, you know what is Lyman series? Lyman series is one in which the transition should complete on n is equals to 1. You know, minimum wavelength for Lyman series will be given by a transition between n is equals to 2 to n is equals to 1. The smallest transition will give you the maximum wavelength. Here is a maximum wavelength, lambda maximum. Whereas minimum wavelength will be given by the biggest transition of the series that always occur between n is equals to infinity to n is equals to 1. So this gives you the minimum wavelength. Defined wavelength, we will say lambda minimum. Therefore, for minimum wavelength, for lambda minimum of Lyman series, n1 is equals to 1, n2 is equals to infinity. So taking this, considering the wavelength expression, that is 1 by lambda is equals to r into 1 by n1 square minus 1 by n2 square. From this expression we can calculate the minimum wavelength and maximum wavelength. So for minimum wavelength, n1 is equals to 1 and n2 is equals to infinity. We will substitute here. In this kind of problems, note that you will be given the Rydberg constant. You can by heart it, you can know it, but still they will give you a Rydberg constant. The Rydberg constant is 1.097 into 10 to the power of plus 7 per meter. It is not minus 7, it is plus 7 per meter. So we will substitute it here. 1 by lambda minimum, to be more specific, let's say even write the kind of the series it is, lambda minimum of Lyman series is equals to Rydberg constant. Let us retain R value till the last step, and later at the end we can substitute the Rydberg constant. 1 by R is 1 by n1 square, 1 by 1 square minus 1 by n2 square. n2 square is therefore infinity square. 1 by infinity is always 0. This term becomes 0. Therefore, we get lambda minimum, take the reciprocal of Lyman series. Lambda minimum of Lyman series is 1 by R. Is therefore 1 by 1.097 into 10 to the power of plus 7. Approximately, right now I am not going to use a calculator, so approximately we will be getting around 0.911 into 10 to the power of minus 7 meters. The denominator we had per meter, it goes to numerator, will become meters. 0.911 approximately, which will therefore become, in terms of angstroms, when we express, it will become 911. 3 times you move the point to the other side, it will become therefore minus 10 into 10 to the power of minus 10 meters, which is nothing but an angstrom. Therefore, lambda minimum is equals to 911 angstrom approximately, without using a calculator. So this approximate value will be coming. Maybe in the third decimal there could be a small change, you can just check that. Similarly, we can go and calculate even the maximum wavelength for, say, lambda maximum, for lambda maximum of Lyman series. I have already explained you what is lambda maximum. It is a wavelength emitted when the transition takes place between n is equals to 2 to n is equals to 1. So for lambda maximum, n1 is 1 and n2 is equals to 2. Right? So the equation is 1 by lambda is equals to R into 1 by n1 square minus 1 by n2 square. Putting the values, 1 by lambda maximum of Lyman series. To be more specific, I am just mentioning what kind of wavelength is it and which series is it, is equals to 1 point, or otherwise, like once again keep R value, R as it is without substituting to the last step for our convenience again. 1 by n1 square is 1 by n square minus 1 by 2 square. So you have 1 by 1 here minus 1 by 4 here. Taking the LCM will be 4 here, and the numerator will be 4 minus 1 will be 3. We have got R into 3 by 4. Take the reciprocal of that. You get lambda maximum of Lyman series is equals to, denominator will become 3R, numerator will become 4. It's 4 by 3R. Therefore, lambda maximum is hence 1.333 divided by 1.097 into 10 to the power of plus 7. So lambda maximum will approximately therefore become 1200. So while dividing 1.333 by 1.097, we'll be getting 1.215, which when we convert into angstroms, we get 1215 10 to the power of minus 10 meters, which is 1215 angstroms, which is say 1215 angstroms. So the maximum wavelength of Lyman series is 1215 angstrom and the minimum wavelength is 911 angstrom. We can write if we need the conclusion also, otherwise even if we leave here, we will be getting the full marks for it. So we'll do one more problem. This problem is an extension of the previous one, almost a similar kind of problem. In the previous problem, I asked you to calculate both the wavelengths, minimum and maximum. In this problem, I will be giving you one wavelength and ask you to calculate one more wavelength. I am giving you like this. The wavelength of the first member of Lyman series is 1215 angstrom. Calculate the wavelength of the second member of the Balmer series. In the previous problem, Rydberg constant would be given to you. Whereas in this problem, Rydberg constant will not be given to you, which means you are not expected to use it even though you know it. You are not supposed to use it directly. Without using Rydberg constant, you should be able to calculate the unknown wavelength. So how shall we do it? We know the expression for the wavelength is 1 by lambda is equals to r into 1 by n1 square minus 1 by n2 square. Some of you may get a doubt that along with r we also had z square. Z square we can include only if it is any other atom other than hydrogen. Since we are doing with Lyman series and Balmer series, only the spectral series of hydrogen. For hydrogen, Z is equals to 1. Since we don't use Z term in the formula. Without Z term only we are using the formula because it's a hydrogen atom. So coming back, now just use the given data here. What is the given data? The Lyman series, the wavelength of first member of Lyman series is given. For first member of Lyman series. First member of Lyman series. For first member of Lyman series, what is N1 value? The N1 value is 1. And what is N2 value? Since it is a very first member, it should be the first transition of Lyman series. For the very first transition, N2 should be 2. So putting these values back in our expression, we get 1 by lambda of first member of Lyman series. You see the way I am denoting this, it is easy for us to write it like this. 1 by lambda first member of Lyman series is equals to, keep r till the last but one step, r into 1 by n1 takes the value of 1, so 1 square, minus 1 by n2 takes the value of 2, therefore 2 square. And you see now, let us take the reciprocal after taking LCM, 1 by lambda 1 of Lyman series. See what is the reciprocal of this? LCM is 4, the numerator therefore becomes 3 by 4, hence it will become 4 by 3r. Let us call this equation, let us number this equation, say 1. Similarly, write one more equation for the unknown wavelength, that is the second member of Balmer series. For second member of Balmer series, second member of Balmer series, for the second member of Balmer series, say N1, since it is Balmer series, N1 would take a value 2, and now you have to think carefully, it is a second member of Balmer series. For first member of Balmer series, the transition is between 3 and 2. For the second member of Balmer series, therefore, the transition is between 4 and 2. Therefore, N2 should be 4. If you had taken N2 to be 3, the member would be the first member between 3 to 2. Between 4 to 2, the member is second member. Similarly, 5 to 2 will be third member, 6 to 2 will be fourth member. So here we are doing for the second member, therefore it is between 4 to 2. Substitute this in the wavelength expression. So 1 by lambda, second member of Balmer series, denoting precisely here, 1 by lambda 2 of Balmer series is equals to r into 1 by 2 square minus 1 by 4 square. Right, now again take the LCM. These are 16 here, 16 4s are 64. Therefore, taking LCM here, lambda 2 of Balmer series is equals to, the 64 goes to the numerator, divided by r is the denominator. 16 minus 4 will be a 12. Let us divide equation 2 by equation 1, so that we get lambda 2 of Balmer series divided by lambda 1 of Lyman series. We are dividing equation 2 by equation 1. So on the right hand side, 64 by 12r multiplied by the reciprocal of the right hand side of the first equation, that is 3r divided by 4. The r can be cancelled. Now we have a 3 1s are and a 3 4s are. So on the right hand side we are left with therefore 64 by 16, hence it will be simply a 4 there on the right hand side. So hence, since we need lambda 2 of Balmer series, lambda 2 of Balmer series is 4 times lambda 1 of Lyman series. Now we can substitute for lambda 1 of Lyman series, which is a given value, which is a given wavelength. So hence, finally, lambda 2 of Balmer series is equals to 4 times lambda 1 of Lyman series is 1215 angstrom, which will be approximately 4860 angstroms. 1215, 2 15s are 4 is 860. Therefore, lambda 2 of Balmer series is a 4860 angstrom. This way, without using the Rydberg constant, we can arrive at the unknown wavelength.